Chapter 20, Network Data. Network data consists of nodes, also called vertices, such as individuals in a social network or companies in a trade network, and edges, the links between them. The links describe the presence or absence of connections among the nodes. Links can be either directed or undirected. A connection from node X to node Y is called directed if Y is a direct successor of X. In this case, the edge from X to Y includes an arrow that points to Y. Covariate information on the nodes, such as characteristics on individuals in a social network, such as gender, age, and race, may affect the absence or presence of connections among the nodes, and such information needs to be incorporated into the analysis of network data. Finding out how certain covariate affects the links between nodes may be an important aspect of investigation. A network of nodes and their interconnections can be represented with an agency matrix. The first example is marriage and power in 15th century Florence. Before we get to that, we can look at a node example, which was found here. Where we have a matrix with 1 through 3. And we have that matrix where we set zeros and ones. And we could plot it just as well to show the ones, twos, and threes and how they're interconnected. So the first example is marriage and power in 15th century Florence. Political ties were established via marriage. The agency matrix for the 16 most powerful families in Florence shown in the following includes a 1 whenever two families were connected in marriage. This agency matrix represents an undirected graph. A graphical representation of the network created with the R package iGraph is shown. The data includes information on families who are locked in a struggle for political controls of the city of Florence around 1430. Two factions were dominant in the struggle. One revolved around the infamous Medicis, the other around the powerful Strozzis. So first we have to load the package and we read the data of Florence, where we have zeros and ones. Then we set the marriage group, and we use this to help function to understand the options for the graph. We set the seed and we plot it. The presence and absence of a network links can be used to measure network connectivity and social importance. A node's degree in an undirected network is defined as its number of edges to other nodes. Medicis are connected. There are connections or edges between the Medici and 6 other families, hence the degree is 6 for the Medici. The Lamberti family, on the other hand, is connected to only one other family, the Guarani. The Lamberti family has degree 1. So you set the data frame. A deeper measure of network structure is obtained through betweenness. Betweenness is a certain centrality measure of a node or vertex within a graph. Nodes that occur on many shortest paths between other nodes have higher betweenness than those that do not. So we calculate and plot the shortest path. Betweenness versus degree. The Medici have the highest degree, or the largest number of edges, but only by a factor of 3/2 over the Strozzis. But the Medici's betweenness, which is 47.5, is 5 times higher than that of the Strozzi, of 9.33. Betweenness measures total graph connectivity rather than counting the next-door neighbors. The Burt structural holes. Burt, of 2004, discusses social capital and how it can lead to brokerage opportunities. His ideas are similar than betweenness, but he puts extra weight on connections to isolated nodes. Isolated nodes or holes can act like bottlenecks in companies, and they lead to unexpected employees having excess power and influence. But if you are the employee, it may be a fast track to promotion. Now we move on to the second example, which is connections in a friendship network. The second example represents a simulation of an in-school friendship network for a school community in the rural western United States, with a student body that is largely Hispanic and Native American. So we load in the library, we load the network object, and summarize the data. There are 203 undirected connections among 205 nodes. The edge list summarizes the unordered pairs of nodes that are connected. The 205 by 205 symmetric agency matrix has zeros in the diagonal. As a node cannot be connected to itself, and many zeros and 2 by 213 ones as its off-diagonal elements. So the network density is given by 2 times 203 divided by 205 times 204, which is equal to 0.0097. Only about 1% of all possible network connections are realized. So we assign numbers to nodes and we look at the grade, the sex, but we do not look at the race in this example. So we're going to use this for the graph later on, where boys by square are 4 sides and girls are 12-sided. We give an agency matrix, and we get the density of network, which is, as we said, 0.0097. The degree of a certain node in an undirected network is obtained by adding the number of connections that exist between the node and all other nodes of the network. StatNet, in its calculation of degree, counts on edge between nodes I and j twice, as it considers both the direction from and the direction to the node. For an undirected network, we divide the degrees that are obtained by StatNet by 2. To make the results consistent with our earlier definition and the results from iGraph, the same adjustment needs to be made for betweenness, as a StatNet sums over all paths that move from one node to the other and vice versa. So we do that, we divide it by 2, and we get a degree of network nodes and the number of connections. StatNet double counts the connections in an undirected network. Edge between nodes I and j in an undirected network is counted twice. So we divide by 2 in order to make the results consistent with our discussion in the text and the output from iGraph in example 1. And we get the degree. Then we do the betweenness of a network. Where StatNet double counts the betweenness in an undirected network, we divide by 2 in order to make the results consistent with our discussion. And we get the betweenness. Now we can plot the degree, we can plot the betweenness, and we can get a histogram of both. A couple of students, for example, the first student on the list, a female 7th grader with 13 connections, are well connected, but most students have relatively few connections. More than 25% of the students are singletons, or have no connections to other nodes, and about 50% of the students have at most one connection. So we're going to plot the degree by betweenness. We're going to get a box plot of degree and the grade, and a box plot of degree and the sex. Females have more connections than males, and 8th to 10th graders have fewer connections than entering 7th graders and students who are close to graduation. We have already shown how to obtain the agency matrix from a given StatNet network object. Below, we show how to export the edge list. We also show how to create a StatNet network objects from first principles when given the edge list or agency matrix. We use fo.mesa.high is already a network object. Below, we illustrate how to create an undirected network from the edge list. First, we obtain the edge list of a network object. The edge contains the edge list. In an undirected network, edge information is stored in second half of fo.mesa.high of mel. We're going to plot the degree again, plot the betweenness, and plot both. So fo.mesa.high is already a network object. Below, we illustrate how to create an undirected network from the agency matrix. The agency matrix has been stored previously in M. And we're going to look at all the graphs again. So we have a visual display of the network. We're going to set C to get a reproducible graph. And we're going to get the plot where we have a generic graph without labels and covariates. We're going to do it again and get a generic graph with labels. And then we're going to do it one more time, where we have 45 rotate squares and isolates are not displayed. Then we do the density of interaction among students from the same grade, ignoring their gender. Then we do a density of interaction among students from a given grade with students from all grades, ignoring gender. Matrix M1 shown below is not square. It has R rows and C columns. The C columns include the R nodes that determine the rows of M1. The number of possible edges in M1 are R by R minus 1 plus R by times C minus R, which is R times C minus 1. The density of interaction among students from the same gender group, ignoring the grade. And now we do the density of interaction among students from a given gender group with students of either gender, ignoring their grade. Then we do the density of interaction among students from the same grade for a given gender. First, we look at the female 7th graders, then the male 7th graders, the female 12th graders, the male 12th graders. The density of interaction among students from a given grade with students from all grades for a given gender. Again, the female 7th graders, the male 7th graders, the female 12th graders, and the male 12th graders. Our plotting options are not that easy and will make pictures look differently. So the principles of Fruchterman and Reingold, they distribute vertices evenly in the frame, minimize the number of edge crossings, make edge lengths uniform, reflect inherent symmetry, and conform to the frame. And we're going to plot all the data that we have shown. Where the last plots should look like this. Where we have the first plot, the second, and then the third put together.